Okay, students, now we are in part 2 of videos. We have seen the effect of slip on rotor frequency, rotor voltage, rotor power factor, rotor reactance in previous part first. Now, let's develop our equivalent circuit. First of all, we should know what is torque. Okay, before making before drawing final equivalent circuit. So torque, there are basically two types of torque that we are dealing. First one is starting torque, another is running torque. Even though at starting also, or when our motor starts running at full rated speed, the load doesn't change. But even though the load is same at start, the torque requirement is high. Under running condition, with the same load at rated speed, the torque requirement will be less because of inertia. So in DC motors, we have seen that the torque is directly proportional to flux and current. So here also the flux is directly proportional to EMF induced on the rotor side. So E2 and I2, and there is a one factor in this induction motor which was not there in the DC motor, is power factor. This will be we will be deriving in further lectures. So more talks are there, like maximum or breakdown torque, developed torque, output torque, that we will discuss in further lectures. Okay, now let's first develop our equivalent circuit of three-phase induction motor. So we will be defining some quantities, that is phi is flux per pole, p is number of poles, where ns is equal to 120 upon p, and as we can see that induction motor can be treated as a stationary motor, that is equivalent to a transformer. The transformer has two windings, primary and secondary. So do induction motor. The primary is treated as a stator winding, which is stationary. The main difference is the secondary winding of transformer is stationary, but our secondary winding, that is rotor side, is moving. So this is the basic difference, and because of this moving nature only, a factor comes, that is slip. Okay. So the induced EMF in stator, that is E1, will be exactly same or can be derived from transformer, that is root 2 pi kW1 Fin volts per phase. But this kW1 factor was absent in transformer, which is called winding factor. This kW1 is called winding factor, which is the product of pitch factor and distribution factor. We have studied this in our construction classes. Now, these are the quantities we have defined. Even in stator induced EMF, you can. This is all written. You can easily read them. No need to again teaching you. Okay, so these are the quantities you can see in these slides, and you can see Kw1. Okay, winding factor of stator. Okay, this is the induced EMF of stator side. And you can see E2 is EMF induced in the rotor per phase when the rotor is standstill. But E2 dash, where E dash comes, it means the motor is running. Okay, at slip S, and slip is change in speed, that is ns minus and r upon ns. Okay, these are the quantities. Okay, now Kw2. Now this Kw1 is the winding factor of stator side, and Kw2 is the winding factor of rotor side. Similarly, root 2 pi can be stated as 4.44. Now rotor induced EMF per phase at standstill, it must be similar to transformer only, 4.44 Kc2 Kv2 F5 of 92. Okay. Now induced EMF per phase in the rotor side when the rotor is rotating at slip S. Nothing will change, only F will become F dash. F dash is S times of F. Kw2 is same, Kc2 into Kd2, where Kc2 is pitch factor, Kd2 is distribution factor. That is, we have studied in construction of windings. Now next, now from equation 1 and 2. So we will be dealing equation number 1 and uh, 2. From equation number 1 and 2, we can see at standstill the ratio of this will become Kw1 N1 upon Kw2 N2, and this ratio Kw1 into N1 is stated as a new term, that is Ne1, or you can say effective turns ratio. Okay, and we will denoting it as A, where in transformer it was even upon, it is N1 upon N2 transformation ratio. So instead of transformation ratio, it is equivalent to that only, but we are there's a one factor multiplied with the turns ratio, that is effective turns ratio of an induction motor. In some cases, it is also called as reduction factor. Now we have defined NE1. What is NE1? What is NE2? You can easily see this. Now the MMF balance in induction motor. First of all, the transformer equivalent circuit, which we have studied in the previous lectures on electrical machine. First, this is the exact equivalent circuit of transformer circuit, and this is the MMF balance equation. N1 I1 minus N2 I2 is equal to N1 I0. Okay, so at standstill, the equation becomes same. Instead of this the equation becomes same, I2 by A. Here instead of N1 and N2, the quantity changes to Ne1 or Ne2. Now stator equivalent circuit. You can see this is the primary circuit of transformer. There is no change in this circuit. And what is this I2 dash? I2 dash is the secondary equivalent circuit, equivalent current in primary side. Okay, and this is my no load load component. Jx5 is my magnetizing component that is used to produce magnetic field, and R is my loss component, or the component referred to stator losses, constant losses. Okay, now rotor at standstill. So the rotor at standstill is similar to transformer secondary only, Jx2, R2, E2, I2. Okay, there is nothing changed in it. Now when the motor starts running, there one factor will come. Instead of E2, it will become S of E2, Jx2 will become J of S of X2. So this is the equivalent circuit when the rotor rotates at slip S. Now when the rotor rotates at slip P, the rotor losses or the power in this circuit will be I square into the resistive. There should be no losses in the reactive part. There will be active losses or active power will be on this R2 only. Okay, so I square R2, and but this power will be seen from rotor side or rotor frequency, but since the rotor is moving, uh, we cannot we can say that we cannot stand at rotor. Okay, so we need to calculate the power seen from the stator side or from our side. So we are just redeveloping the circuit. Just divide the whole circuit with S. You can see the E2 will become S of E2 will become E2, Jx2 will become X2, and R2 will become R2 dash by X. This is a simple KVL equation. You can see it is understandable. Okay, I'm writing this I2 in the form of polar S of E2 upon R2 plus Jx2, S of E2 angle 0. So we need to take some reference. So I am taking E2 as my reference. E2 will be 0 degree, and the angle R2 and X2 will share will be tan inverse S of X2 upon R2. Now from circuit, this is the equation, KVL equation, simple. Divide by S. What I've said, the equation will be rearranged, and the circuit will become this. Now the power will be I square into R2 by S. Now this will be the power seen from stator side or from our side. The final equation is this. Nothing. This equation I2 and this I2 are similar. Nothing has changed. Only just divide this R as this. The same equation will appear. Now the final circuit referred to stator side will be this. I have referred. You can refer the circuit from as as we referred in transformer. But the equivalent circuit referred to primary. The equivalent circuit referred to secondary. So here also we can refer our circuit to stator as well as rotor. But the beneficial part for us will be to refer the final equivalent circuit referred to stator side. So this R2 dash, Jx2 dash, this is mechanical load equivalent. You know? Nothing has changed. R2 dash, it is a combination. Just add these two terms, add R2 dash plus R2 dash 1 by S minus 1. You will be getting R2 dash by S. This only. What is this dash? This means this is the secondary reactance or rotor side reactance refer to stator side. You can see R2 dash is A square R2, X2 dash is A square X2, and I2 dash is I2 by A, where A is Ne1 upon Ne2, that is reduction factor or effective turns ratio. Okay, this is the final equivalent circuit referred to stator. Okay, after this we will be continuing our lecture in part third. Thank you.